Hello everyone, welcome to this remote interview, mock interview for mathematics. I am Dr. Tom Crawford. I'm one of the maths tutors at St Edmund Hall, and this is my colleague, Professor Nguyen, who is also a maths tutor at St Edmund Hall. So we are going to be conducting a mock interview with one of our second year students to give you a feel for what the interview process looks like. Generally, we're just going to be working through an interesting maths problem with both myself and Luke adding some hints and tips and helping guide the candidate in the right direction. We're not in any way trying to catch anybody out. We're generally just trying to work together as a team to try and solve an interesting maths problem. Luke, did you have any other thoughts or anything to add?
Yeah, just about the general view of how an interview is going. So we are going, as Tom was saying, we are just going to do some math problems together. As a candidate, one shouldn't be worried if one gets stuck in an interview. Just keep thinking and keep pressing at it. We tutor will input and then help you along the way. We'd like to know more about you. We're not trying to see the bad of you, but we want to see how you struggle, how you deal with a math problem. So that's the general way how we go about an interview.
Brilliant. And hopefully it should be an enjoyable process for everybody. That is ultimately what we are genuinely trying to do here. And you will probably get the best experience of seeing what we mean by that by watching the mock interview that we're about to begin.
Hi, Bethan. I'm Luke Nguyen, one of the tutors at Study Hall, and joining us today is Dr. Tom Crawford, another tutor here. So we're going to do a conversation in mathematics. So the way it goes is that we're going to ask you a question, and then you're going to give us what you think about it, and hopefully eventually arrive at a solution. Along the way, if you get stuck, we will give you some input on how to proceed or how to help you think. So don't panic, just keep pressing on that problem. Eventually we'll get there. Okay, so before we start, can you say a couple of words about yourself?
Hiya, yeah, so my name's Bethan. I'm from Cambridge, and I'm really interested in probability and stats within maths. I really like how, especially probability, you can come up with some really, really pretty kind of solutions to problems, but they're always so useful kind of in applying them in stats. Like you can really see kind of where it's useful in the real world as well.
Okay.
So unfortunately, we won't be doing any probability or stats today. However, we're going to do a problem that I hope you will agree is pretty. So I'm glad you did mention that. So the way it's going to work is we have this interactive whiteboard, which I will be able to draw on. So I'm going to start by just drawing this square, which should hopefully appear on the screen for everybody. And you yourself, Bethan, will be able to annotate this, and that will also be visible to both myself and Luke. So we're all kind of working on a shared document live. So, you don't need to worry about holding up anything. Just get all your thoughts down on here. And of course, you can speak to us as well. Now, the reason I drew a square is that's actually going to be the starting point of our problem. And what we're interested in doing with this square is filling it with rectangle shaped tiles. Now, there are obviously lots of different rectangles that we could use. So we're going to slightly limit it and say that the rectangles have to be in this ratio where the long side is twice the length of the short side. So the ratio of all the rectangles has to be 2 to 1. Now those numbers can be anything. So it could be 2 to 1, it could be 4 to 2, it could be 1/2 to 1/4. Just the ratio has to be 2 to 1. Because the idea is we want to fill the square with a certain number, let's say n, rectangles. So for a simple example, I've drawn a square here. I could take two identical rectangles like that. So again, the square can be any size. We can shrink the square. We can make the square bigger because, of course, the only key thing about the square is that all the sides are the same. So here, for example, this would be an n equals 2 tiling. We have filled our square with 2 of these 2 by 1 rectangles. And what we were interested in trying to work out is for what other values of n can we fill the rectangle? So which n tilings are possible? And a final thing, so before you sort of jump in, is just to say the rectangles do not all need to be the same size, right? So the example I've given you has 2 rectangles in this particular size. You could use 6 rectangles with 3 in one size, 2 in another, and 1 in a third different size. That's all okay. They just have to have this aspect ratio of 2 to 1.
Okay.
So as I said, in general, we just want to know for which n can we do this, can't we do this? It's a very hopefully wide-ranging kind of open problem for you to have a think about.
Yeah, that sounds really interesting, actually. Okay, so I think straight off the bat, my instinct is that because it's integer values of n, I always think of like an induction kind of a proof. So I think I'm probably going to start with trying out a few kind of smaller values of n, see if there's a way I can kind of put the squares together to, I don't know, yeah, like find some sort of trick that I can keep building off of ones I already have. I think.
Yes.
Okay, so right, so for n equals 1, see if I can get it to work. Okay, so n equals 1.
There we go. Yeah, we can see that.
That doesn't work, obviously, because like it's a 1 by 1 square. You can't put 2 by 1 square, 2 by 1 rectangle in that. And then, so yeah, n equals 2 is fine.
Yeah.
That's good. Okay, so then for n equals 3. So I'll try and fit some together. I'm not sure if 3 would work really. It doesn't seem like it's.
Yeah, can you explain why?
Yeah, so anytime you're doing this, there's always going to be one rectangle that's the top left corner, right? So maybe I'll say this corner. So this is, I'm not going to put any like this side or this side.
Yeah.
And then I'm either going to have to put one here, which is going to be like any size. Or maybe it could work, I don't know. And then, so if I say this is a one by, or maybe a 2 by 1 rectangle, then this can be x by 2x.
Yeah.
So then this length is going to
Well,
be.
before you move on, does it always have to be, for the top side, does it always have to be 2 or more than 2? I mean, 2 rectangles, right? So just to cover the top side, do you need at least 2 rectangles, or you need fewer? Or
I think you can just have one, but I think in this case I could just rotate it, kind of rotate it this way, and then I can take this like x by 2x rectangle to be the top side anyway. So I think I don't need to consider that case.
Okay.
Sorry, my tablet's just gone. Right, it's coming back. And then, yeah, so then this distance is 2x minus 1. And this distance is going to be 2 plus x. So yeah, so that's never going to be double.
Why is the bottom one 2 plus x?
Oh, sorry, yeah. Oh, that's just 2, isn't it? Just 2. So then, oh yeah, I guess if I could put 2x minus 1 equals 2, then
equals.
Oh, equals 4. Sorry. equals 4. Equals 5. And then x equals 502. So actually, yeah, if I had it being, oh, but wait, that doesn't work. 4. Oh no, so this would have to be 4 anyway. Wait, I'm 4 by, wait, what am I doing here? That doesn't work.
Well, so you've worked out a potential value for x, and as you said, it looks like this is going to have to be 2 and 4. And you're right in that
Yeah.
one would have to be 4. So then what can you say about the other side of the square? So you know the left-hand side, you know the total length now of that left-hand side.
Oh yeah, so then it will be a 5 by, oh yeah, so this one's going to be, wait, what's that going to be? That one's going to be 5. This one's going to be 5 over 2 plus 2. Oh, well, maybe it's not going to be 2. Wait, sorry, I'm confusing myself. I'm not quite sure what I've done.
Yeah, no rush. Just keep
Oh, is that?
on.
Okay, so that's 1 by 2, and then that's x and 2x. So 5, and that means it's 5 by 3. 5 by 3. 2x equals.
So I
Is
think
it a square?
Yeah.
Yeah, sorry, what was that?
Is it a square? You've
square?
worked out.
Yeah, and then it wouldn't be a square. So
good,
yeah,
because you know x, don't you? Because you've said the right-hand side has to be 5. I mean, you kind of got there, but didn't perhaps put the pieces together, right? You worked it out. You'd sort of figured out that x had to be 2.5. So then the top length is 4.5, and the right-hand side is 5. It's not a square.
Yeah, not a square. There's no way I can
So it's not
make it a square. Yeah. Yeah.
Okay, great. So I think at least I'm happy enough. So 3 isn't possible, and I think that was a reasonable argument to say why. So right, so if we go back to your list, we've said that 1 we can't do, 2 we can do, 3 we can't do.
Can't do. And then 4, I think. Let's have a think. So again, I'll just start with 1 in the corner. And then if I were to kind of put 1 like that, just kind of, there might be a 1 which actually does work. Oh wait, I don't know how to get rid of that. Okay. 3, 4. No, that's not going to work, I don't think. Because that'd be 1.5, and then that's 1. Yeah, so that wouldn't work because that'll be like that. Or I could do. One, 2, 3. Oh no, they don't have to be the same size, do they? Sorry, I'm just kind of having a mess around at the moment.
No, this is good. This is what you should be doing. Yeah.
Okay, sure.
So
I think if I did that, it's probably not useful now, but I guess I could use that as the.
That's useful for something else. Yeah. So that pattern is useful for some things, but not for the case n equal to 4, but it's useful later on. Yeah,
that one can be for later, not for now.
Why is it potentially? Why do you think it's useful for later?
Well, because I've left a little square, so I think that's what I can use to maybe go by induction. And if I were to find another
So what
one.
statement would that give you? So suppose that we look at that configuration. So what does it say about the possible value of n?
So if I find any n that does work, then I can add 4 to that n as many times as I want to. So,
So that would be useful. So maybe you want to write it down to return to it later.
Yeah. So it's going to be n0 plus 4 n, pretty much.
Yeah.
And then actually, if I could find something that's co-prime to the 4, so without any common factors, then I think past a certain point, then all integers would work.
Yeah, well, we return to that later. We just want to keep this in mind. Let's press on with the case n equal to 4.
Sorry, I'm getting a bit ahead of myself. Is there one that should work, or am I looking for a counter proof to it?
Maybe you want to think back about the case n equal to 3. Just try to have a more robust way of arguing why n equal to 3 doesn't work, and maybe that can say something about n equal to 4. Think about a corner.
Okay, right. So do you mean like along the top side? I guess I can have any number up to, well, technically up to 4 of rectangles at the top. But
so
I think,
how many corners can you fit into a rectangle? So imagine that you have 3 or 4 rectangles sitting there. Then you look at the corner. You have 4 corners. Yeah. So what's the relation between the number of corners and the number of rectangles that you look into?
oh, okay. So in each rectangle there's 4 corners, and then for
we're looking at the corners of the original square. You have only 4 corners of the squares. And then you have now 4 rectangles.
Oh, so there's going to have to be... Wait, sorry, I'm not quite sure what you're getting at with that.
So where should those original corner of the square belong to? How many of them? Well, I don't know. Try to find a relation between the original corners and the little squares that you have. Sort of, where each of the corner belongs to.
So if you think, Bethan, if you say we have a square and it has 4 corners, and now you're limiting yourself to saying I have a maximum of 4 rectangles. So obviously there is a sort of finite number of solutions in terms of how many corners each rectangle can touch in your square.
Right, okay. So
for example, could each rectangle touch 1? Could you have 1 rectangle that touched 2 corners? And what would that mean for what was left?
Right, that's interesting. Yeah, okay, so each rectangle is either going to be in 1 or 2 corners, and it can't be any more than that.
Why not?
Because if you had all 3 corners, then there's like not really any space to put another rectangle, and it's going to be a 2x1 shape.
It doesn't fit in the square, right? You've turned your rectangle is hanging out of your square, basically.
Yeah, basically, yeah. Oh yeah, so if I'm thinking of it like that, and if I want it to touch all 3 corners, then it's got to be outside of the rectangle.
It's going to hang out, yeah.
So you have only either 1 or 2 inside a rectangle, or maybe none.
Okay, so if I'm if I'm going to say that this one maybe is touching 2 of the corners, then I have kind of another 2x1 to fill with 3 rectangles.
Yep.
Is that possible?
I think, well, you can't just stack them together. That wouldn't work. Because the dimensions would be off.
Yep.
You can't just have one that's, oh yeah, again, you can't just have one that's touching 2 of the corners, because then that will be the whole thing.
Yeah.
So each of them has to touch 1 corner, but there's only 3 rectangles, so that doesn't work.
Yeah, what about the case one? You know, each rectangle contain exactly one corner.
Okay, and then so that would be the case of one. So yeah, I can't really have two like that because then if I were to put any this side, then this wouldn't be a corner.
Mm.
And if I was to put any this side, then that wouldn't be in the corner either, this one. So I would have to stack them like this in order to have two in a corner. And then that applies to all the corners as well, because like they're not really unique corners. So yeah, that leaves with this kind of arrangement, and that leaves the square in the middle. So that's, yeah, so 4 doesn't work either.
Okay, good. So we've got, I'm happy enough with that. So we've got 1, obviously we can't do, 2 we can do, 3's a no, 4's a no. It might be helpful to have something else that we can do at this point.
Yeah.
Sure, yeah. I guess I could just put some rectangles together and count them. Yeah. Put them together until they make something good. Okay, so I've got 1, maybe I'll do 4 together and then like that, which is square. I think that's a square, so that'd be 2, 1, 1, and then, oh, my thing's gone up again, and then a half times 4. So yeah, that's a square.
Yeah.
So 5 does work.
Okay.
Good.
And that automatically means we have from the thing with the 4 back here, that means we automatically have 9, 13, 17, and any number added on.
Should we start keeping a track of these lists?
Oh yeah.
So what kind of integer have you?
Is this a prime number?
No, not 5. You said 5 and then 5 plus.
Oh yeah, so that's any 5 plus 4m for any integer m.
Okay. Yeah.
Yeah, and then yeah, so
Don't forget that you had another number that you could do previously.
oh yeah, and then also 2 plus 4m.
Yeah.
And then that's like half of the the numbers past 5 anyway, because 2 and 5 are both different values when you kind of with like modulo 4 in like.
Is it half the cases?
Sorry?
Is it half the cases or not quite?
Yeah, because it's a multiple of 4 plus 2 and a multiple of 4 plus 1 at this point. So yeah, we just need to find a multiple of 4 plus 3 and then a multiple of 4 plus nothing.
Yeah.
So if I find a multiple of 4, then it'll be any multiple of 4 past a certain point. So yeah, so that I can just put four of the blocks of 2 together. So that's the same block. These are all the same block of 2. So there's 2, 4, 6, 8. So this is a block of 8. Does that make sense? What I've drawn?
Yes.
Yeah.
I think so. You're just taking the original one we had of 2 and then just doing 4 copies of it. I think is.
Yeah. So then this is an 8 plus 4.
Yeah.
And then I just need to find one which is a.
So that leaves what?
Multiple 4 like plus 3. Okay. So maybe I could try 7 or something, but I'm not sure if that's easy to do. 7.
Yeah, if you manage 7, then you manage all, right? Is that?
Yeah. So if I manage 7, then I can manage all of them past 6. I think past 6.
Well, you already did 6. You already did 5.
Yeah, I mean, so if I can find 7, then that means I've got all integers past 6.
5.
You have 5 as well. You drew one earlier for 5.
Oh yeah, of course, yeah. So all integers past 5. So for 7. Yeah, so again, I guess I could try with having this one in each corner. Maybe I could try that, and then oops, 1, 2. So then that's 2 by 3, and then I need another one here. Maybe another one here. One, 2, 3, 4, 5, 6, and then does that make 7? I don't know if this will work. So that's 1, 2, 3, 4, 5. This is 5 by 4. Oh no, that's not a square. I don't think. Yeah, that's not a square.
So 7's quite a difficult one to think about. 7 is possibly the hardest integer to look at. So I wonder whether we can. So I really like your approach of using modular arithmetic and saying if we get certain remainders, modulo 4, then as you've said yourself, if you can get 7, then you're done. Or maybe if you could get 11 or 15, then you would have all the numbers past that point. Now I wonder whether there's another possible way of constructing these rectangles. So you came up to earlier the thing that you starred when you said, oh, I can put 4 around the outside of a square. And that's why you were doing this discussion about plus 4m.
Mm-hmm.
Now, there is actually another way of generating higher values, which isn't modulo 4. It's modulo a different integer. And that can be very helpful to rule out a lot of these remaining cases without having to worry about 7.
Sure. Okay. If I can find something that's odd, then that automatically gives me the answer, because then 4 and this odd number, if I can find one, wouldn't have any common factors. So then I can always kind of construct them in a way that makes any integer.
Yes,
so,
past a certain point, like you said, yes.
Yeah, so if I can find the 3, I think before I found something with 3 that maybe made a square. Okay, maybe if I can have one here, another one here, and oh, that's not going to make a square.
So remember here, rather than trying to find a specific solution, you're trying to find a method, like you said, sort of like of induction, being able to generate more rectangles.
Yeah.
So I might suggest if you go back to the very first one that I drew of the 2 rectangles. Now, from that configuration, is it possible to, let's say, divide it up into, starting from that configuration, but kind of divide it up to get a different solution, a possible number you already have, but using a different method? If that kind of makes sense.
I'm not sure. Wait, so so using a number I already have. Wait, could you explain that again? Sorry, I didn't quite.
Right.
So if you look,
sorry, go ahead.
I was just going to say, so the example. So we go back to my drawing of 2, and let's see if I can use a different color to highlight this for you. So let's do this in blue. So you sort of started with these 2, and then you had this really good idea about saying, well, I can just always add these ones around the outside.
Mm-hmm. Yeah.
Right, and then that was kind of like I think of it as like a building up method. You can take a solution you have, and you can always add 4, and that's how you were generating all of these other ones that you had. Now I'm saying, is there another way of, instead of like adding 4 by doing something, could you add another number?
Right. Okay.
To create that kind of sequence.
Sure. Yeah.
In a similar manner, and starting with 2 is hopefully a helpful place to begin.
Okay. Okay. So maybe if I can put 1 here that kind of overlaps there, and 1 there. One, 2.
Yeah, that could lead to something. Yeah.
3, and then then that's not a 2 issue.
You're basically back where you were with the last one.
Yeah. I keep on getting back to the same configuration. Oh dear.
Instead of adding them on, can you like divide up the ones that we already have? So instead of adding, so like you've added up, or I call it the building up method of adding these 4 around the outside. Can you take the configuration you have, maybe focus on one of the rectangles? Can you divide that up into smaller rectangles such that you get a configuration that works?
Oh, right. Okay. That's good one. Yeah, so if I can divide one of the rectangles into a different number of rectangles, then...
You've actually already done it in your solution for n equals 5. So if you compare your n equals 5 solution with your n equals 2 solution, maybe we can put them next to each other. If we draw them next to each other.
Oh, sure. Where's my x solution? Oh, okay. Oh, of course. I can just... Oh, yeah. That's... I can't believe I missed that. Okay, so it's just...
I don't think I explained it very well either, so that's my apologies too. So what's happening? What's happening going from the 2 case to the 5 case? What is it that you're doing there?
You're adding 3 to go on to 5.
Perfect. So how does that help us?
So that means you can also have any so anything you already have. So say 2 plus 3 m. Yeah, and then you can also, so if we say that n3 because it's multiplying by 3, and then to have well, I'll put this as n as well, and then n plus 4 m4, because 3 and 4 are co-prime, then that means you can just
I think let's go back. We already said that we already have the 3 plus 4k that remains. So now you just learn another way of settling it. Can you find something? Does that give you something or not quite? Right, so if you manage any multiple of 4 plus 3, then you would get all the bigger number, right? So what have you managed?
So any integer past 5, I think. If we assume that 7 works, then that means
no, we didn't know that 7 works.
Oh, okay. Oh, right. So,
but now you just learn a new trick. So does it say anything about this multiple 4 plus 3 or not quite?
So at the moment we don't have 7, which means we don't have 11 or 15 or 19 or 23 from your original method of adding 4s.
Mhm.
However, we now have a new method of adding 3s. So can we get any of those numbers?
Oh yeah. So you can add 4 and add 3 to things. So so for every
So what would be the lowest one that we can get now? Because it's not 7 yet.
Oh yeah. So we've got the smallest would be. So wait, what was the number of ones? We've got 2, 5.
Yep, you had 5. Yep.
Did
6.
we have? We had 6 as well, didn't we?
Yeah, that's 6.
Yep.
Yeah.
6, then
Now
8.
We've also got oh, do we have it? Oh yeah, we have 8 as well.
Yeah, I think the only thing that we care at this point are 7, 11, 15, 19, and so on and so forth. So which one of those can you solve?
So for 11, what we could do is 8 plus 3.
Yeah.
Perfect.
So 8 with this kind of unadded. And then
so that means that
15.
Yeah.
We can do for, how would you do that? So you could put 6 plus.
No. You had 2 methods of generating. Either you add 3 or you add.
Yeah, sorry, I'm just trying to like work out which one you add together to get 15.
What are the 2 methods that we generate new numbers?
You add 3 or you add 4. Like any number of times. I don't know why I can't quite see it though. Wait, so the
you just showed us. You just showed us you can do 11.
Yeah.
Right. Good. There we go. So you just showed us. So that was the new thing, right? 11 was new because that plus 3 method allowed you to take your drawing of 8,
of course,
add on 3, and then there's a lot going on, don't worry. And then you said, oh, but we can just keep adding 4. So now you've got 11, 15, 19. You've got them all. So it all comes down to, rather than being left with like a quarter of the numbers, you now literally just have 7 as the only remaining one. Now there was a reason I sort of stopped you when you were thinking about 7 earlier, because 7's really hard. 7 is possible, but we are pretty much out of time. So I didn't want you to spend all of the remaining time trying to figure it out, because it took me a very long time to do it. But I will show you the solution just before we go, because I'm sure you want to see it. So 7 is possible, which, and I'm going to attempt to draw this now, is going to look like, so you have a big one at the top. Now I have to remember this. You have these sort of smaller ones along here. And then, so that's now 4. You need 3 different sized rectangles. And then I think you have 2 more of these small ones. And then that big one, like that. So I think that will be true for 7. So you can, let's check my numbers. So what that's going to
take a 6 by 6 square.
Yes, that's a better way to do it. Thank you, Luke. I should have drawn this using the actual squares on the app, but that one should work if you think of it as a 6 by 6, 6 by 6 square. You can figure it out, and you've got 3 different sized rectangles there to get the 7. Sure. So, yeah. So the answer to the question. What was the answer to the question? Because we said, for what values of n can we tile the square with 2 by 1 rectangles? What's the final answer?
I think we got it was any integer greater than 5 or 2 as well.
Yes. Perfect. So it's I find it surprising that you can do it for almost every single number apart from just 3 of them. Awesome. So just before we go, do you have any final questions for us, or anything that you want to ask at this stage? You don't have to, just your opportunity in case there's anything that's unclear.
I think that's all clear for now, but yeah, thank you very much.
Okay. Thank you. I hope it was fun.
Yeah, thanks a lot, and good luck.
Thank you, Betham. Bye-bye. So now that the interview has concluded, we of course will have a very brief chat amongst ourselves as tutors to check that we agree on the candidate's performance. So Luke, how did you think that in general went, and what were you looking for from a candidate there?
Yes, I quite like how the interview went. It's clear that at the beginning the candidate struggled quite a bit and made some silly mistakes, which we probably don't care about.
Nope.
What has clearly shown us is that the candidate didn't have prior knowledge of the problem, was trying hard to solve it, and she kept pressing at it. Eventually arrive at a solution. We can clearly see the thought process at which the candidate arrived at the problem. I think that she has shown that her enthusiasm towards mathematics.
I think she definitely enjoyed the process. That was something that came across to me, which I think as interviewers is something that's always really nice when you have a candidate that is actually having fun, because as we mentioned at the beginning, we want, you are meant to enjoy this process as much as is possible in the circumstances. It is just, three of us as mathematicians kind of working together to try and solve a problem. I think you made a very good point about the beginning. Obviously, she was a little nervous, a little flustered about trying to figure out the sides of the square, but we don't really care about that. Like you said, that's not what we're looking for in these interviews. It's that thought process and that ability to be creative and to spot patterns. So I think being able to see the relationship between the drawings and realizing that you can continue to add 4. So, that was spotted very early on, and it was really nice to see the candidate then see the use of that. So not just realizing that we can add 4, but immediately see, oh, that allows us to generate a sequence. So I think that was a really, really good thing to see. And yeah, the kind of thinking definitely that we're looking for in a candidate. So yeah, I think overall, I think that was a good interview.